Just make stuff up.
Yeah, it's true. I agree. Physics is simpler than all the other crap that people invent.
Yeah. That's why we're scared to learn physics, so
Especially psychology.
define what I'm not doing. Well, like, we can't. Yeah.
Psychology.
I don't know.
So
Psychology of science?
It's psychology is not,
Is psychology of science? That's
and if it's not, is neuropsychology a science?
I think
this is a physics class. Why are we talking about these?
We're talking about the merits of the other sciences, so we can say that we're better than.
one of my physics is better.
Wait, so it's not.
Brazilian.
Oh, I didn't think of.
Purely because.
Pecans, cashews, peanuts.
Oh, cashews not enough. I mean, through Mendeleev.
Fun atomic physics.
Peanuts also not enough. I'm not kidding. Should look it up.
Okay, was it tomato or fruit?
It's like.
No, we're not talking about tomatoes, we're talking about the most powerful.
Physics is on.
These kind of acorn in the world. Yeah, acorns are nice. Only got 3. You're gonna fail.
It's like there's like.
November.
A lot of things discovered like.
It's not that you can do more than that.
Yeah, it's still a lot of. It's only like that, so you see.
Fail.
The first comment is.
Anyways, that's why you could figure it out.
Not every person so I have not tried it. I have not heard of it. Since.
All right, so let's get started. Last lecture before the break. So what we've been talking about are these logic gates that we'll use to process digital signals. So for example, here is the NAND gate. It has 2 inputs. And 1 output. We constructed truth tables by listing all the possible combinations of inputs on the left, and then on the right, we list the corresponding outputs. The NAND gate was special because we can use it to build all of the other gates that we talked about. So that includes the inverter, the AND gate, the OR gate, the NOR gate, XOR, and XNOR. I should point out that it's also true of the NOR gate. If you had a collection of NOR gates, you can use them to assemble all the other gates as well. So what I want to do today is I want to get you finished getting prepared for tomorrow's lab. We talked a little bit already about some of the things you'll do in the lab tomorrow. One of the things you'll do is you'll just confirm the truth table for one of the gates that's available. And the ones that we have available are just the inverters and the NAND gate. So you'll choose one of them. You'll assemble the circuit. These things need power to operate. So you'll have to figure out using the data sheets, where does the power get connected and where does ground get connected? Which pins on the chip correspond to, say, the inputs of a particular NAND gate, and where's the output? We also talked about monitoring the output using an LED and a resistor. So you would connect, for example, an LED to the output, and then put that through a current limiting resistor and then connect it to ground. This resistance is something like 200 ohms. Its value is not super critical, but something like that. And so when the output is high, we'll have 5 volts here and a current going through your LED, and it will turn on, it'll shine red. And when the output is low, we'll have 0 volts here, no current through the diode, and it'll be off. Okay, so What I want to start with so that's the first thing you'll do in the lab. The second part of tomorrow's lab is to take 3 NAND gates and combine them in a way that they will perform the OR gate operation. And then so you'll design, build, and then test your OR gate made out of only NAND gates. So the third part of the lab is about the flip-flop, and so that's what I want to start with today. The way that we'll begin is we'll just notice that so far, all of the logic gates that we've talked about, their outputs are determined by the instantaneous values of the input. And so what I mean by that is, let's suppose that we were in the state where the inputs were 1, 0, and the output of our NAND gate was high. So our LED is on. And then what we do is we switch B from 0 to 1. The moment we do that, the output will switch. And so the LED will go off. And then if I take input B and I take it from 1 back to 0, the output will instantaneously come back on and our LED will be shining light. So what I want to do today is talk about this flip-flop, and it will have the property that its output will be determined by the history of the inputs. And so in that sense, it will have some memory capabilities. And so we'll see explicitly what that means. So first, we'll just make some comments that so far, all logic gate outputs depend on the instantaneous states of the inputs. What we want now is to design a device that has some memory capability. Okay, we're going to build it using NAND gates. And the device we're going to build is called a flip-flop. In particular, it's called the RS flip-flop. There's a few different variations of flip-flops. The RS1, the R stands for reset, and the S stands for set. So our device is going to have 2 inputs. The inputs are going to be reset and set, and the output will tell us something about the history of those inputs. So the RS flip-flop is a 2-input device. So those inputs, as I said, are R and S, with 2 outputs actually. So the state of the outputs, we're going to call the outputs Q and Q bar. This notation, before we write anything else down, this notation is pretty suggestive that one output will just be the inverse of the other. And so that's going to be true when Q is high, Q bar will be low, and vice versa. When Q is low, Q bar will be high. So the state of the outputs tell us, or let's say tells the user, which of R or S was the last to be low. Okay, so that is the flip-flop, in some sense, remembers which of the 2 inputs was last to be low. So what that means is, if if you had one of these flip-flops, it has two inputs. I could be out of the lab, you could be messing around with those inputs, doing whatever combinations of low and high you want. And then I come back into the lab and I could just look at the outputs and I can tell you, without having been in the room, which of the inputs you last had low just by reading the output. And so that's the memory capability. So let's draw what it looks like. It's not that complicated. It's only it uses two NAND gates, but they're combined in a special way. So there's our two NAND gates. I'm going to take one input from the top NAND gate. I'm going to call that S, and I'll take one input from the bottom NAND gate, and I'm going to call that R. So that's our reset. The output of the top NAND gate will be Q, and the output of the bottom one will be Q bar. And so we just have to connect the remaining two inputs, and the way they're connected is like so. So the output of the second NAND gate feeds to the input of the first, and the output of the first NAND gate feeds into one of the inputs of the second. And they look like this. So this is the RS flip-flop. And so what we're going to try to do is we're going to try to analyze this circuit and show that it has this property that we talked about, this memory capability. Okay, so to start, let me just write down the NAND gate truth table. So something that we can refer to as we go through this analysis. All right, so the truth table, the possible inputs for a single NAND gate. So this is not the truth table for the flip-flop, it's just the truth table of a single NAND gate. And the NAND gate is always high, except for the output goes low when both inputs are high. All right, so the first question that we're going to try to address are, what are the possible outputs for Q and Q bar? Okay, so let's see, we'll just list all the possibilities and then we'll see which ones are allowed and which ones are not allowed. Okay, so there's all the possibilities. I'll move my truth table over just a little bit. So, all right. So what we're going to do is we're going to have some default states for S and R. We want a device that tells us which one was last low. So what we're going to choose to do is we're going to say that usually S and R will be high. And so we're going to set S and R both equal to 1, and then we're going to see which of these outputs is allowed. So we'll take SR equal 1, 1, i.e. both high. As the default state for the inputs. Okay, well, okay, so we'll do that. We'll say this is 1 and this is 1. And let's just try these outputs one at a time. So is it possible for Q and Q bar to both be 0? Well, let's see. If Q bar is 0, that means the second input of the top NAND gate is also 0. And so then we go, okay, so the inputs of this top NAND gate are 0, 1. And when I have 0, 1 or 1, 0, the output's high, which is a contradiction. Okay, and so that's not allowed. Okay, so we cannot have Q bar equal to 0, 0 when SR is equal to 1, 1. All right, fair enough, no problem. So we'll say, all right, those outputs clearly are not allowed. Let's skip ahead to this last one, 1, 1. So what happens if I make Q and Q bar both 1? Well, it's a similar type of reasoning. If Q bar is 1, that's connected to the input of the top NAND gate. So we also have a 1 here. And when I go to my truth table, when I have 1, 1 as my inputs, I need a 0 at the output. We have another contradiction. And so once again, we have excluded one of these possible output states. So we also cannot have Q bar equal to 1, 1 when SR is equal to 1, 1. All right. So we've excluded already half of the possible outputs. Let's try the others. So what do we have? We have 0, 1. All right. So then we would have a 1 here. And we go 1, 1. I need a 0. Oh, that worked this time. So then if Q is 0, then we have a 0 at the second input of our bottom NAND gate. And so now we have 0, 1. The output has to be 1. And it is. So that works. So this one is allowed. You might be able to see already that the other possibility will be allowed as well, but let's just go and confirm that. So now we need a 1, 0 here, put a 0 here and a 1 there. 1, 0, 1, that's good. 1, 1, 0, 1, 1, 0, that's good. So 2 of these possible states are allowed for an input combination of S and R both being high. Okay, so we can make some comments about that. We can say when SR is equal to 1, 1, the output of the flip-flop has 2 possible stable states. And so we could say that our output is bistable. So there's 2 possible outputs, and so there must be some kind of condition that determines which one our system falls into. And that condition is going to be the history of the inputs. So let's see how that works. All right, so the question we have is, what happens if one of S or R momentarily drops to low? Okay, so we said that our stable or default inputs are going to be 1, 1. Let's just start with 1, 1. We'll choose an output. It doesn't matter which one we choose. We'll choose one of the 2 possibilities, 0, 1 or 1, 0. And then we'll see what happens when we change an input. Okay, so let's pick some initial conditions. We'll do case number 1. So case 1, let's pick some initial conditions. We have to have a starting point. So we'll say S is 1, R is 1, Q is 0, Q bar is 1. All right, these are our defaults. This, I just picked one of the stable states. We'll do the 1, 0 case. Well, the 1, 0 case, we will do that after this one. So we'll do both cases. All right, so let's go put those states on our flip-flop. So S and R are 1. And Q is 0. And Q bar is 1. That's the initial conditions. And we've already confirmed that that is indeed a stable combination of inputs and outputs. All right. So what I want to do is I want to take one of these inputs. We'll take S and we'll drop it low. So we're going to take S and we're going to say, okay, you go low. And let's see what happens when we do that. So we're going to take S to go to 0. All right. Now, we're starting with Q bar is 1. So we're starting with a 1 over here. Okay, so we start with 1. So when we take S to 0, now the inputs to this NAND gate are 0, 1. And the output should be high. Okay, so we started with a 0, so it must be that what happens is we now get a 1 at Q. Okay, well, let's put that in. So Q goes to 1. All right. Well, what else is going to happen? So now Q was 0, but it's 1 now. And so we end up with a 1 over here. And so we were at 0 initially. And then it became a 1. All right. If it becomes 1, now we have 1, 1 at the input to the second NAND gate. The output should be 0. It's at a 1 now, so it's going to transition to 0. Okay. So Q bar changed its state. So that means Q bar went to 0. R, we didn't touch R, we just left that alone. Okay, so what we know so far is taking our S to 0 for this particular case caused the outputs to change. What I'm going to do is I'm going to take my S input and I'm going to let it return back to high, back to the default state. And we're going to see what happens for R, Q, and Q bar. Okay, so we momentarily took S from high momentarily to low, but then we return back to high. Okay. We have to be a little bit careful here. We said Q bars change states, and so this 1 became a 0 over here. So it's 0. And then when we now we're at 1, 0. 1, 0. Okay, it just stays at a 1, it stays high. Okay, so this stays high. So Q stayed high. What we can do is we can say when we return S to a high state, Q remains at 1. All right. If Q remains at 1, then we went from 0 to 1, and then we stay at 1. If we stay at 1, and this was at 1, then we haven't changed the inputs to this NAND gate, and so there's not going to be a change to the output. This is going to stay at 0, which means this stays at 0. So everything just remains the same after we take S back to high. So we end up with a 1 here, and we end up with a 0 over here. All right. Or so this has some of the features that we wanted. The feature we wanted was that the output is going to be determined by which of the inputs was last to be low. We've constructed this picture where we said S is now the last one to be low, and the output is a 1, 0. So the summary of this little analysis is when S is last to be low, Q bar is equal to 1, 0. Let's try another case and see if this sort of behavior continues. So we're going to pick some different initial conditions. We'll start with S and R in their default states, but what we'll do is we'll take Q and Q bar to start at 1, 0. So we're starting in the second of the bistable output states. And we'll play the same game. We'll let S go from 1 to 0, and we'll just go through the sequence of logic and figure out what happens. Okay, so I'm going to erase all of this stuff. And we'll start again. Okay, so we're going to start at 1, 1, and we're going to take S to 0. Our outputs are going to start at 1, 0. That's the opposite state that we chose last time. Let's just make sure. 1, 0, yes. Okay. So our starting point is 0 here and 1 here. And now we start these transitions. So if we go from 1 to 0, we're at 0, 0, and the output is 1. It was already at 1, so it just stays there. So this just stays at 1. That means this input stays at 1. Well, if it was already 1, 1, and the stable output is 0, it's just going to stay 0. So this stays 0, and this stays 0. And so taking S low for this second case does nothing to our outputs. And so this is going to stay at 1. This stays at 1. This stays at 0. Okay, so the next step is just to return S to its default value of 1. So we let this come back to 1. So we're going to end up with 1, 0. The output's 1. It's already 1. And so, again, nothing changes. So this is going to stay 1. The inputs of the second NAND gate haven't changed, and so its output won't change either. And so basically, what we found here is no change in this case. But if we take a look at this comment, when S was last to be low, Q bar is 1, 0. Here, clearly, S is last to be low because R was never low in our sequence of steps. And so we get 1, 0 as our output. This comment is still valid for case 2 as well. And so we can take this comment, copy it, and paste it over here. And we can say that it is still the case that when S is last low, Q bar is equal to 1 0. This should be a Q bar. Did I just miss it from my copying? Probably my copy didn't work. All right. So we've confirmed that. What do you suppose will happen if R was last to be low? What's the output going to be? 0, 1. Yeah, exactly. And so I'm not going to go through all of these steps, but you can follow the exact type of analysis and you will find that R last low implies Q bar is equal to not 1 0, but 0 1. Exercise for the students. Show that regardless of the initial states of Q bar, right? It could be 0 1 or 1 0. For either of those cases, allowing R to go temporarily low resets the output to Q bar is equal to 0 1. All right. Good. The circuit that you're going to build in the lab tomorrow is just a very slight variation of this. And so let me show you what it's going to look like. So the circuit you will build in lab number 7 is a lot of it is exactly the same. So do this. Okay, this will be Q bar. This will be Q. So this is exactly the circuit we just analyzed. The only change that we're going to make is we're going to put inverters at these two inputs, and we're going to call this S and R here now. Let me add one more thing to this figure. We talked about last time that using LEDs is convenient to monitor the outputs of logic gates. And so that's true here as well. So here's my LED connected to output Q. And here is the Q bar LED. We can connect them together and then we can feed them through a single resistor, something around 200 ohms. All right. So we know that Q and Q bar can only be in the 1 0 or the 0 1 state. And so what we should expect when we build our flip-flop is that we will see only one of these LEDs on typically. One on and one off. So without the inverters in place, what we said is that the output was determined by which of S or R was last to be low. So we typically hold S and R at 5 volts. Whichever one drops to low will determine what the output looks like. So what's going to be different here when we put the inverters in place? Instead of the outputs determined by which is last low, what will the output be determined by?
When it was last high.
Which was last high, that's right. The other difference is that the default states for S and R are not going to be 1 1, they're going to be 0 0. So we'll start with them low. and whichever one was last high will determine the state of the output. If S was last high, we'll get 1, 0. If R was last high, we'll get 0, 1. Okay. So with the inverters in place, the default state of the input is SR is equal to 0, 0. The output is determined by which of S or R was last high. So if S was last high, then Q bar is equal to 1, 0. If reset was last high, then we get the other output, which is Q bar is 0, 1. And so this is the behavior that you're going to look for in part 3 of tomorrow's lab. All right, any questions about that? Okay. So we've got maybe 15 minutes left. And so what I want to do with the rest of the time is I want to talk about sort of like what are some of the virtues of digital electronics? What benefit does it have over analog electronics? So digital electronics. So to answer that question, what I want to do is I want to consider the following noisy signal. Okay, and so what it's going to look like is this. This is some voltage, okay, that we're trying to measure maybe. And so as a function of time, if we monitor that voltage on an oscilloscope or something like that, let's imagine that it was pretty noisy and it looks like this, and then there's a sudden kind of change, maybe it goes negative a little bit, and then kind of comes into a bit of an intermediate range between where it was before. Okay, so this is a voltage signal with large fluctuations. So what we're going to end up doing is we're going to define, this is going to be a problem, so I'm going to get rid of that big spike at the end. What we're going to end up doing is we're going to define some thresholds, and we're going to compare our voltage as a function of time to those threshold levels. So in digital electronics, we define a high or a 1 as anything greater than some threshold, which I'm going to call threshold 1. And I'm going to draw that threshold on our diagram. And so we'll make threshold 1 this red voltage here, something like this. So threshold 1. And just for the sake of argument, let's say this is something like 2 volts. And so what we would do is we would say, look, anything above this threshold will interpret as a high. So as a logical 1. It doesn't matter that maybe here the voltage is 0.3, over here it's 6, and over here it's 4.2. All of those points correspond to a digital 1. And so already this is giving us a sense of some of the benefits. It offers some immunity to noise. This is a noisy signal. If you were to ask me, what is the analog voltage? I'd have to say, oh, it's changing all the time. I could tell you what an average value is, but that's about it. But in digital electronics, if you ask me what's the state of our system, it's in a high state. I don't care that the voltages are fluctuating all over the place. It's always above the threshold, at least for this duration. And so we have a stable high. Okay. We're going to define a low or a 0 as anything below a threshold 2. We're going to choose a different threshold because I'm going to fix this up a bit. The reason we're going to choose a different threshold for the low is because if we had a noisy signal that was crossing this first threshold all the time, then we would have a problem where we would say, oh, it's flipping between high and low constantly. And so that's maybe not what we want. So let's make a second threshold voltage, something like this. And I'm going to call this threshold 2. And, you know, just for the sake of argument, we'll just assign some value 0.8 volts. And so whenever I'm below 0.8 volts, I have a stable low. And so from this range of values, we're always below the second threshold. And so we're always in a low state. Okay. That leads to the possibility of a signal that sits between the two threshold values. So that's happening at the end of our plot here. And all we can do is say that those are undefined. I cannot interpret those signals. So signals between thresholds 1 and 2 are undefined. So we get some noise immunity by defining our thresholds for low and high signals. So we have a stable digital output, even, maybe I shouldn't say output, stable digital signals or states, even with large voltage fluctuations. Okay. Now, the limitation, of course, is that we have only two states, a 0 or 1. So how are we going to pass kind of useful information? So what we have to do is, because I can't, say, pass an arbitrary voltage of 5.3 volts or something like that, I need a way of kind of transmitting that kind of information. And the way we're going to do it, the only possibility is to pass a sequence of digital values that can change from 0 to 1. And then the receiver of that information will have to interpret that sequence of data or bits and convert them into more useful information. And so we're going to use binary numbers to do that. Binary numbers you may have come across before, especially if you've taken some computer science. So in binary numbers, we have only 2 digits. And those digits are 0 and 1. This is also just the base 2 number system. Okay. The decimal system that we're used to is the base 10 system. And in the base 10 system, we have 10 digits. And they are 0, 1, 2, 3, up to 9. Once we've used up those 10 digits, we need to include a second digit in our number. And so we start, that second digit can be any of 0 to 9. Okay, so how can we work in this base 10 system? So we can represent any, we'll start with base 10 because that's the system we're used to, and then we'll write down an equivalent analogous way of handling numbers in base 2. So can represent any base 10 number in the following way. Okay, so let's say I take the number 153. I'll put a little subscript here to say that I'm going to represent this number in base 10. So one way I can do it is I can say, well, it's 100 plus 50 plus 3, but I could write 100 as 1 times 10 to the 2. And then I can write 50 as 5 times 10 to the 1. And then I can write 3 as 3 times 10 to the 0. And so I can break my number up into different powers of 10, and I use my digits as coefficients in front of those powers of 10. All right. So in the same way, we can express binary numbers as, well, okay, so let's say I'm just going to pick a random binary number. Binary numbers can only have the digits 0 or 1, so they're just going to be sequences of zeros and ones. And if I want to figure out what this is equivalent to, I can just expand the number out in the exact same way. This time, instead of multiplying powers of 10, I'm going to take these coefficients and they're going to multiply powers of what? 2. Yes. So the most significant digit is out here. So this would be a 1 times 2. And so to what power would it be? This would be the 10 or 2 to the 0 power. This would be the 2 to the 1's place, 2 to the 2, 2 to the 3's place, 2 to the 4. So this is 1 times 2 to the 4 plus 0 times 2 to the 3 plus 1 times 2 to the 2 plus 1 times 2 to the 1 plus 0 times 2 to the 0. Okay, and so what is this equivalent to? 2 to the 4, 2, 4, 8, 16. Okay, so it's 1 times 16 plus 0 times 8 plus 1 times 4 plus 1 times 2 plus 0 times 1. And you add them up, and we get 22. So 1, 0, 1, 1, 0 in base 2 is equal to 22 in base 10. All right, 153, if you wanted to write 153, okay, in base 10, it would be 1, 0, 0, 1, 1, 0, 0, 1, base 2. So what I need is 1, 2, 3, 4, 5, 6, 7, 8. I need 8 bits to represent a number of 153 in base 10. So this is an 8-bit binary number. One of the other things you're going to do, the last thing you'll do in the lab tomorrow is you're going to work on assembling a counter. A counter is something that takes in a clock signal, some square pulses, and every time there's a transition from high to low, it increments your count by 1, and it counts in binary. And so what we're going to do is we're going to send in a train of clock pulses, and that will cause your counter chip to count in binary 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, and so on. So let's just list off a bunch of binary numbers. And once you get used to it, the way they count is pretty straightforward. You just increment the least significant digit 1 at a time. So this one will always be incrementing, like so. And then when we go from 1, 1, and we increment this, we get a 0 here, and then we're going to add 1 to this. But I can't add 1. I can't have a 2 in a binary system. So what happens? Instead of a 2 here, what do I get? 0, and then what happens to the next one? 1, right? It's like a carry. 1 plus 1 is 0, carry 1. All right. And so this would continue in this fashion. So I guess we would end up with, let's see, 1, 1, 1. This would be 0, 0, 1. 0, 0, 1. All right. This is decimal 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We could confirm that we got this right because this would be 1 times 2 to the 3, which is 248, right? And so this is the first 10 binary numbers. Okay, so we've run out of time, but if I wanted to send someone some information like, say, 5, then instead of sending 5 volts, what I could send is a high, low, high, and as long as my person who's receiving that information, we have to have some kind of convention. We'll have some convention that when you see a certain sequence of bits, that's going to indicate starting the transmission of data, and then I'll transmit my data, and then there'll be a different sequence of bits that signals that the transmission is over. And so you look between the code for start and end transmission, and in there you'll have the useful data that you want to interpret. And all we have to guarantee is that the data that we send lies either above threshold 1 to represent a high, or below threshold 2 to represent a low. All right, good. Thank you very much. Have a good afternoon, and we will see you tomorrow.